high-alpine harvesting to fully automated sawmills, this is timber handling at its most advanced. Watch telescopic cranes work on steep mountain slopes. Material handlers move massive logs with precision, and intelligent lines debark, cut, and sort every piece for maximum yield. From forest to construction-ready systems, nothing is wasted. This is modern wood processing, engineered for efficiency, safety, and total material control. The CBogen 718E series is deployed by LAU Forest Service GmbH of Austria, a specialist contractor known for cable yarding and timber harvesting in some of the most demanding alpine environments in Europe. Operating in steep, remote mountain forests requires more than experience alone. It demands compact, powerful machinery that can perform reliably at elevation while maintaining the highest safety standards. For LAU Forest Service, equipment choice is critical, and only proven solutions are added to the fleet. This newly commissioned 718E series marks the fifth CBogen telescopic timber crane operated by the company, reinforcing a long-standing trust in the brand's performance and durability. The compact crawler design, combined with a strong telescopic boom and highly responsive load control, allows the machine to operate confidently in confined mountain work zones. Whether supporting cable yarding operations, handling heavy logs, or managing roadside processing, the 718 delivers precision and stability where margin for error is minimal. The machine entered service in the Pitzel Valley at an altitude of around 1,600 meters, an environment where terrain, weather, and ground conditions constantly test both operators and equipment. Here, the 718E series demonstrates its strength through a robust undercarriage, impressive lifting capacity, and refined operator ergonomics. Together, these features ensure dependable performance, improved efficiency, and sustained productivity, making the CBogen 718E series a key asset for high-alpine forestry operations. The CBogen 830 Electro and 835 Mobile are purpose-built material handlers engineered for demanding timber handling operations, and their deployment in Turkey demonstrates their versatility across industrial yards, sawmills, and portside environments. Designed to manage heavy, irregular timber loads, both machines deliver the stability, precision, and continuous reliability required in high-throughput operations where efficiency and safety are paramount. The CBogen 830 Electro is optimized for stationary and semi-stationary applications such as sawmills, log yards, and timber terminals. Its electric drive system provides high torque with significantly lower energy consumption, reduced operating noise, and zero on-site emissions. This makes it especially well-suited for facilities focused on sustainability and long-term operational efficiency. With its extended reach and high-capacity grapple, the 830 Electro supports fast and accurate log sorting, stacking, and in-feed operations, maintaining consistent material flow while minimizing environmental impact. Complementing this, the CBogen 835 Mobile brings flexibility and mobility to dynamic timber handling tasks. Mounted on a wheeled undercarriage, it can move quickly across yards or terminals without the need for auxiliary transport equipment. Strong lifting performance, rapid cycle times, and finely tuned hydraulic control allow the 835 Mobile to handle large diameter logs and bundled timber safely and efficiently. Its elevated, ergonomically designed cab offers excellent all-round visibility, improving operator awareness, comfort, and productivity throughout long shifts. This focus on efficiency and material control is reflected further at Dalvidi mill, where timber processing operates as a tightly coordinated, performance-driven production system. Incoming logs are carefully measured and digitally scanned to capture their full geometry, allowing sawing patterns to be optimized for maximum recovery and product quality. Logs are then processed through advanced sawing lines that combine chipper canters, profiling systems, and circular saws to extract the greatest possible yield from every stem. After cutting, timber flows through inspection, drying, grading, and finishing stages before receiving preservative treatment. Throughout the entire process, Dalvidi mill adheres to a strict zero-waste principle, ensuring that every component of the log is utilized. Bark, chips, shavings, and sawdust are redirected into secondary markets or used to fuel the kilns, creating a closed-loop system that maximizes value, efficiency, and sustainability across the operation. At Dalby mill, timber processing operates as a tightly controlled, efficiency-driven production system, designed to maximize yield, product quality, and total material utilization. Every stage of the operation is integrated to ensure that raw logs are transformed into high-value structural timber with minimal waste and consistent performance. The process begins as incoming logs arrive on site, where they are weighed, measured, and digitally recorded. This initial data capture provides full traceability, supports accurate production planning, and forms the foundation for process optimization throughout the mill. Once recorded, logs are transferred to the in-feed of the log sorting line, where advanced 3D scanning technology analyzes each piece of timber in detail. The system captures precise information on volume, diameter, taper, curvature, and overall geometric shape. Using this data, optimal sawing solutions are calculated for every log, ensuring the highest possible recovery while meeting structural and dimensional requirements. This digital assessment allows the mill to adapt to natural variations in the raw material while maintaining consistent output quality. Following scanning, logs are organized into dedicated storage bins and scheduled into batch production runs based on size, class, species, and product demand. In the sawing line, a combination of chipper canters, profilers, and circular saws converts each log into structural products with exceptional efficiency. 2 chipper canters first square the log into a central cant. This cant is then profiled along its sides as boards are removed by circular saws before being rotated and reprofiled to extract additional boards and a central core product. This multi-stage approach ensures that maximum value is recovered from every log. Finished boards move to sorting lines for visual inspection before being pinned, banded, and transferred to storage. Timber is then dried in kilns, with drying cycles ranging from 100 to 190 hours, depending on species and section size, until a target moisture content of 18% is achieved. After drying, timber passes through strength grading, where visual assessment is combined with X-ray technology and moisture measurement to verify structural performance. Planing lines then refine surface finish and edge profiles before final preservative treatment in automated pressurized plants. Operating on a strict zero-waste principle, Dalvidi mill ensures that every part of each log is utilized, creating an efficient, closed-loop production system that maximizes value and sustainability. The Miore debarking line, equipped with the SLH debarker, integrated sorting, and automated cross-cutting system, represents a highly advanced solution for preparing roundwood for modern sawmilling operations. Designed to operate reliably under industrial conditions, the system combines automation, precision measurement, and adaptive control to deliver consistent log quality while maximizing material recovery and production efficiency. Its capability to handle large diameter timber makes it particularly well suited for high-capacity mills processing mixed species and variable log profiles. At the front of the line, the pre-positioning roller conveyor establishes the foundation for stable and predictable material flow. Incoming logs are aligned, centered, and evenly spaced before entering the debarking zone, ensuring controlled movement regardless of log size or surface condition. This stabilization phase is critical when processing heavy or irregular timber, as it reduces rolling behavior, mechanical shock, and uneven loading on downstream components. By ensuring each log enters the system in a controlled orientation, the conveyor contributes directly to both process reliability and equipment longevity. As logs transition into the debarking section, the fully automatic SLH debarker becomes the operational core of the line. This unit is engineered for high throughput while maintaining exceptional surface quality. Using integrated sensors and intelligent control logic, the debarker evaluates each log in real time, assessing parameters such as diameter variation, taper, bark structure, and overall surface condition. Rather than relying on fixed operating values, the system continuously adapts its processing speed to the characteristics of each individual log. This adaptive speed control is essential for balancing productivity with quality. Logs with thicker or more fibrous bark are processed at optimized speeds to ensure complete removal, while smoother or thinner barked logs move through more quickly. The result is a consistent debarked surface that meets sawmill requirements without excessive fiber loss. By adjusting to real-world log variability, the SLH debarker minimizes waste while maintaining high line efficiency. A key feature of the system is its precisely adjustable debarking depth. Cutting tools are dynamically positioned to remove only the necessary bark thickness along the entire length of the log. Because bark thickness often varies from butt to top, this automatic adjustment prevents overcutting and protects valuable wood fiber beneath the surface. Preserving fiber integrity improves sawing accuracy downstream and increases overall recovery, especially when processing high-value or large-diameter timber. At the same time, reduced cutting forces translate into longer tool life, lower maintenance frequency, and improved operational uptime. Once debarking is complete, logs pass through the integrated butt-end reducer. This unit addresses one of the most challenging aspects of roundwood processing: oversized butt ends and root flare. Using measurement data collected earlier in the line, the reducer automatically calculates how much material must be removed to bring the log within acceptable diameter tolerances. Excess material is trimmed precisely, producing a more uniform log profile that improves handling and alignment in subsequent sawmill equipment. Uniformity at this stage plays a critical role in downstream efficiency. By eliminating excessive diameter variation, the system reduces the risk of jams, misfeeds, and alignment errors in sawing lines. This not only improves production stability, but also enhances cut accuracy, tool performance, and overall product quality. The butt-end reduction process operates seamlessly within the line, without interrupting material flow or requiring manual intervention. Following diameter correction, logs are automatically positioned for crosscutting. Advanced sensors and programmable logic controllers ensure that each log is accurately indexed to the optimal cutting position based on length requirements and production parameters. This automation eliminates the need for manual measurement or handling, significantly improving operator safety while delivering repeatable accuracy across all log sizes. Precise positioning also supports tighter length tolerances, which is increasingly important in high-performance sawmilling operations. Crosscutting is performed by a heavy-duty industrial crosscut saw designed to operate reliably under continuous load. Built with a rigid frame and high structural stability, the saw delivers clean, square cuts even when processing hardwood species or large-diameter logs. With a maximum cutting capacity of up to 900 millimeters, the system comfortably handles oversized timber that would challenge conventional equipment. Low vibration, precise blade control, and robust mechanical design ensure consistent cut quality and long service life. Throughout the entire line, integrated sorting logic adds another layer of operational flexibility. Logs can be automatically directed based on diameter class, length, or specific production needs. This allows the debarking line to function as more than just a preparation system. It becomes an active contributor to mill-wide optimization. By grouping logs according to sawing strategy or product requirements, the system supports efficient batch production, reduced changeover time, and improved yield planning. From a broader technical perspective, the Miore debarking line is defined by its emphasis on automation, adaptability, and material efficiency. Real-time measurement and automatic decision-making reduce operator dependency while ensuring consistent output quality. Mechanical components operate in synchronization with digital control systems, allowing the line to respond instantly to changing log characteristics. Energy consumption is optimized by matching processing intensity to actual material demands, rather than operating at fixed maximum settings. In summary, the Miore debarking line, equipped with the SLH debarker, integrated butt-end reduction, automatic positioning, and heavy-duty cross-cutting, provides a comprehensive, future-ready solution for modern sawmills. It delivers high-quality debarked logs with precise dimensional control, efficient handling of large-diameter timber, and seamless integration into high-throughput production environments. By combining advanced automation with robust mechanical engineering, the system forms a reliable and profitable foundation for efficient wood processing operations. The Raver WD-1400 log debarking machine is a heavy-duty, high-capacity solution engineered to meet the demands of modern industrial sawmills and primary wood processing facilities. Designed to handle virtually all wood species, the WD-1400 operates across an exceptionally wide diameter range, from 200 up to 400 millimeters. This capability makes it well suited for mills processing mixed timber assortments, including large diameter and irregular logs. Combining robust mechanical construction with advanced control technology, the machine delivers consistent debarking quality, high throughput, and minimal wood fiber loss under continuous industrial operation. At the heart of the WD-1400 is a system featuring stepless regulation of both log rotation and longitudinal feed speed. This allows the debarker to continuously adapt to changing log characteristics such as diameter variation, taper, bark thickness, and wood hardness. By dynamically synchronizing turning speed with feed movement, the machine achieves complete and uniform bark removal while preserving the integrity of the underlying wood surface. This precise control directly contributes to higher recovery rates and improved downstream sawing accuracy. The machine is equipped with optical log detection, enabling automatic recognition of log position, geometry, and movement. Data captured by the sensors is used to adjust tool engagement and processing parameters in real time, ensuring consistent performance even when log quality varies. Adjustable debarking thickness further enhances precision, allowing only the required bark layer to be removed, and reducing unnecessary material loss. A two-step regulation system for debarking head height ensures accurate tool positioning for both small and large diameter logs. To manage oversized butt ends and root swell, the WD 1400 offers end butt reduction with head blocking or an optional reducer from below, producing a more uniform log profile and improving efficiency in subsequent processing stages. Operational control is supported by an integrated video monitoring system, while an air-conditioned operator cabin provides a safe, ergonomic working environment. Automatic bark separation, combined with a dedicated in-feed ramp and out-feed box, ensures smooth material flow and clean handling. Optional features such as a wood scanner and remote control further enhance automation, making the Raver WD 1400 a highly adaptable and technologically advanced debarking solution. The Gablock concept proves that home self-construction is now accessible to almost anyone. Lightweight blocks made from OSB panels and graphite EPS insulation are CNC machined with millimeter-level precision, then assembled by simple stacking and screwing. This modular system significantly reduces weight, simplifies handling, and enables the construction of a complete house in as little as 3 months, compared with nearly a year for traditional building methods. Gablock is a modular self-build construction system developed in Belgium in 2019, created to fundamentally simplify and accelerate the structural phase of residential construction. Designed for both experienced builders and first-time self-builders, the system replaces traditional masonry and complex timber framing with a precise, factory-engineered block solution that combines structure and insulation in a single element. The result is a highly controlled construction process in which speed, accuracy, and predictability are achieved through careful planning and standardized execution. Before any on-site work begins, the construction process is already largely defined. Architectural drawings provided by the client's architect are analyzed and converted into a Gablock-compatible structural layout. This step does not alter the architectural intent. Instead, it translates walls, openings, and load paths into a modular block logic. Every exterior wall, interior partition, corner connection, and structural intersection is mapped in detail. Door and window openings are fixed at this stage, ensuring that their final dimensions are known well before construction starts. This early definition removes a major source of uncertainty commonly encountered on conventional building sites. Once the structural model is finalized, the full construction kit is manufactured off-site. Each Gablock block consists of structural OSB panels combined with EPS insulation, creating a lightweight yet rigid element that fulfills both load-bearing and thermal functions. The blocks are produced in standardized sizes and variants, allowing precise combinations while maintaining simplicity. Every block is labeled and indexed, corresponding directly to the assembly documentation that will be used on site. In parallel, a detailed installation plan is prepared, presenting the entire building as a sequence of numbered components, similar to a large-scale assembly manual. With the kit delivered to the site, construction begins only after the foundation slab has been completed and verified. The slab serves as the reference plane for the entire structure, and its accuracy is critical. Once the surface is clean, level, and within tolerance, layout lines are marked to define wall positions, corners, and axes. These markings guide the placement of the first row of blocks and ensure that the building footprint is established exactly as engineered. The first day of construction is dedicated entirely to installing the base layer of Gablock blocks. This phase is the most critical of the entire build, as it defines the alignment, geometry, and vertical accuracy for everything that follows. Precision at this stage ensures that the structure develops exactly as engineered. Each Gablock block weighs approximately 7 kilograms, allowing it to be handled easily by a single worker without the need for lifting equipment or heavy machinery. Blocks are placed directly onto the prepared slab and connected through a precision-engineered interlocking system. The assembly process is completely dry, requiring no mortar, adhesives, or mechanical fasteners. As each block is positioned, it locks securely into adjacent units, immediately creating lateral stability and maintaining consistent spacing across the entire footprint of the building. This interlocking action ensures accuracy while allowing the structure to stabilize as it grows. Throughout this initial stage, alignment is continuously checked and verified. Because this system does not depend on curing materials, any minor adjustments can be made instantly, without delays or material waste. Once the first layer is completed and confirmed, the exact shape and dimensions of the building are fully established. From this point forward, construction progresses vertically, with confidence, predictability, and consistent precision. As construction progresses into the second and third days, walls are built upward by stacking additional layers of blocks. Each new row interlocks with the one below, maintaining structural continuity and load transfer. The stacking process is repetitive and intuitive, allowing rapid progress without specialized skills. Structural rigidity increases naturally as the wall height grows, eliminating the need for extensive temporary bracing. Door and window openings are formed directly during stacking. Because these openings were precisely defined during the engineering phase, blocks around them are placed according to the plan without cutting or modification. Lintels and reinforced elements are integrated at predefined levels, ensuring structural integrity while maintaining a clean, uninterrupted workflow. One of the defining characteristics of the Gablock process is the simultaneous integration of insulation. Each block already contains EPS insulation, meaning the thermal envelope is created as the walls are assembled. This ensures continuity of insulation across walls, corners, and junctions, significantly reducing the risk of thermal bridges. Unlike conventional construction, there is no separate insulation phase, no variability in thickness, and no dependency on on-site workmanship for thermal performance. Interior and exterior walls are typically erected in parallel. This balanced approach maintains even load distribution and ensures that structural connections between walls are completed progressively. This system's inherent precision allows interior partitions to align perfectly with exterior geometry, simplifying later installation of floors, finishes, and services. By the fourth day of construction, most projects have reached full wall height at ground floor level and, where required, on upper stories as well. At this point, the building begins to clearly take shape, and the structural logic of the system becomes fully apparent. Interfaces for intermediate floors are already defined within the design, allowing the transition between levels to be executed efficiently and without modification. The Gablock system is engineered to integrate seamlessly with standard timber floor structures, eliminating the need for custom detailing or complex adjustments on site. Load-bearing zones and support heights are predetermined, ensuring that floor elements align precisely with the wall structure below. This level of planning allows floor components to be installed quickly and accurately, maintaining structural continuity while minimizing installation time. Once the floor structure is in place, wall assembly continues above using the same stacking principle, with no change in method, tools, or working rhythm. This repeatability supports steady progress and reduces the likelihood of errors as the building height increases. As the structure rises, the benefits of dimensional predictability become increasingly evident. Wall heights remain consistent, opening positions are fixed, and structural interfaces align exactly as intended. This consistency simplifies coordination between trades and removes much of the uncertainty typically associated with on-site construction. Rather than reacting to unforeseen issues, the build advances as a controlled, well-orchestrated process. With fewer variables to manage, crews can focus on execution rather than problem solving. Planning assumptions hold true throughout the project, material flow remains uninterrupted, and construction progresses with confidence. The result is a building process defined by clarity, precision, and reliability, where speed is achieved not by rushing, but by eliminating inefficiencies and uncertainty at every stage. By the fifth day, the majority of wall construction is complete, and the structure has reached its full intended height. Final wall layers are installed with precision, ensuring continuity across all load-bearing elements and confirming that the structural system performs exactly as designed. Door and window openings are now fully defined, giving the building a clear architectural identity and allowing subsequent trades to plan their work with confidence. At this stage, the building has taken on its final volumetric form. The spatial layout is clearly readable, and the relationship between walls, floors, and openings is fully established. Unlike traditional construction methods, there is no waiting period for drying, curing, or material settlement. The system delivers immediate structural stability, allowing the project to progress without interruption. This readiness accelerates the overall construction timeline. Roofing, floor completion, and enclosure works can begin immediately, maintaining momentum on site. By eliminating downtime and uncertainty, the process remains predictable and efficient. The result is a solid, stable structure that is fully prepared for the next phases of construction, demonstrating how speed, reliability, and precision are achieved through intelligent system design rather than compromise. On the sixth day, the structural shell of the building is complete. Both exterior and interior load-bearing walls are fully assembled, creating a continuous, stable framework that is ready to support the roof structure. At this stage, the building has transitioned from a vertical assembly into a fully defined structural envelope. Because all critical dimensions were fixed during the engineering and design phase, there are no deviations on site. Roof contractors can work directly from precise measurements, eliminating the need for adjustments, corrections, or compensatory detailing. This dimensional certainty significantly reduces installation time and ensures a clean, efficient handover between construction phases. The roof structure itself is based on a prefabricated A-frame timber truss system with an accessible attic space. Each truss is engineered in the factory according to exact load calculations, taking into account permanent loads such as roofing materials, as well as variable loads, including wind and snow. This ensures that forces are transferred efficiently and evenly into the supporting wall structure below. The A-shaped geometry provides excellent structural stability while making efficient use of the roof volume, creating usable attic space without additional structural complexity. Trusses are delivered to site pre-assembled and positioned at regular, predefined intervals along the wall plates. Mechanical fixing points and standardized connections allow rapid installation while maintaining consistent alignment and spacing. Integrated bracing elements ensure lateral stiffness across the entire roof structure, contributing to overall building stability. Because the system relies on repetition and factory-controlled accuracy, on-site work is reduced to positioning and securing components rather than assembling them from scratch. In conclusion, the Gablock construction process represents a highly structured and efficient approach to residential building. By transforming the structural phase into a controlled modular assembly sequence, it achieves rapid construction without compromising accuracy, strength, or performance. Within approximately 6 days, a complete structural shell can be erected, providing a stable, insulated, and dimensionally precise foundation for all subsequent building stages. This approach demonstrates how modern construction can combine simplicity, predictability, and engineering rigor to redefine the way homes are built.